In the previous video, we discussed what a differentiation formula ought to do for us. And now we're going to look at some basic ones that we can use in a lot of different cases. First up, there's what's called the constant rule. And so we're looking at functions like f of x is 5. It's the most boring functions where no matter what input you get, it always just says 5. So when you graph them, they're the ones that are horizontal. There's horizontal lines. Well, based just geometrically speaking on the ideas of tangent lines, this tangent line is going to be horizontal. It's going to have slope 0. And so it seems like they should always be 0. Geometrically, that makes sense. So geometrically, we're thinking that the derivative of a constant function is going to be 0. Based on that, that also works out in the limit as well. And this is how we would really check that intuition, is that the derivative of a function c, where now rather than writing a 5, I'm going to write my 5 like that, and it could actually be any number I want, any number, not an infinity or anything like that. But dxc, well, that's f of x plus h minus f of x over h, and we take that limit as the h goes to 0. But if f of x is just always going to give us c, well, we replace all the x's. Well, there's no x's to replace, and so the limit we're looking at here is a c minus c over h. So we're looking at the limit of 0. Well, at least this is the same as 0 when h isn't 0. So it's 0. Voila. That is our constant rule. Whenever we have a constant function, we have we know what the derivative is going to be. It's going to be 0. There's geometric intuition. There's the analytic version of it. And so here is our constant rule. The derivative of just a number, a constant function, is 0 for any constant c. All right. Well, let's look at some more interesting functions. If you've worked through a lot of differentiation via limits, you start to see a pattern for when you're looking at derivatives of functions of the form x to a power. That's just some number there. So we're looking at power functions in general, which are just f of x equals x to the n for some number n. This includes even fractional powers and negative powers, negative fractional powers. Those proofs are a bit more complicated, but we'll start off by looking at powers that are whole numbers. So if you did the derivative of x, for example, that's x to the first. Well, geometrically, that is, we're talking about the line y equals x, whose tangent line is just itself, and so that ought to be 1. Or you could go through, do the limit as h goes to 0 of x plus h minus x once you do all the work through all of that. F of x is just x, so I'm not writing the f's. All right, well, that's just the limit of, go through the cancellations, h over h, so that'll just work out to be 1. That's as we were hoping for. All right, that's not terribly interesting. Let's take a look at x squared. All right, well, that'll be x plus h squared minus x squared over h. The way we want to go about this is expanding that out. And when you expand that out, you get x squared plus 2xh plus h squared minus x squared. All right, well, just like this x and that x canceled, this x squared and that x squared canceled. This has all h's in it. What we end up looking at is the limit as h goes to 0 of 2x plus h. H goes to 0, so that just ends up being a 2x. Okay, let's take a look at the x cubed. Now we're looking at x plus h cubed minus x cubed over h. And so when you expand that out, you end up getting x cubed plus 3x squared h plus 3x h squared plus 3h cubed minus the x cubed all over h. Right? Again, those add up to 0. I'm left with just stuff that has h's in it. In fact, I have something with 1h, something with 2h's, and something with 3h's. And so by the time the cancellation happens, the thing with just one h is left, and then everything else, even after cancellation, still has h's left over. Those things go to 0, and I'm left with just the 3x squared. And that will actually always happen for whole number powers. This mess gets messier and messier, but it always looks the same. And that's thanks to the binomial theorem that if you've got x plus h to the n, this is the binomial theorem. When you expand that, you're always going to get this, x to the n plus n times x to the n minus 1 times h to the first. And then everything else is going to have more than one h in it. It's going to be, well, I'll do it more generally, n times n minus 1 times x to the n minus 2 times h squared. It'll be n times n minus 1 times n minus 2 over 2. Oh no, this will be over 2. This will be over 6, 3 factorial. And it'll keep going. This will have an h cubed in it, and so on and so on and so on. So that means that once I take that x to the n minus x plus h to the n minus x to the n, that's going to cancel off. I'm going to get this much that has a single h in it. And then everything else is going to have one or more h's in it. I could take an h out, but these will still all have an h in them. And so when I divide by h, that h will go there. It'll cancel with that as well. These all have h's in them left over. Those bits will go to 0. And all I'm left with post limit going to 0 is n times x to the n minus 1. And where this n came from is really coming down out of the binomial theorem and Pascal's triangle, where this is when you're raising to the second, or to the first power, second power, third power, fourth power. That's actually a 6, 1, 5, 10, 10, 5, 1. But if you look down this column, you're always going to see the number of that, or that diagonal, the number of that diagonal. And so these numbers correspond to the things that go with one less than the full complement of x's. But anyway, that's where this n is coming from. This n minus 1 is coming from it being the second term in that series, the first one canceling out. And the fact that there's nothing else is because there's lots of h's in every other term. This Pascal's triangle argument works for positive whole number n's. But Newton had this wonderful theorem called the general binomial theorem that actually says, well, you know what, this will still work when n is a fraction. And it'll still work like this. Now, the issue is that this will actually keep going off to infinity. It won't actually stop if n isn't a whole number. It won't stop at x to the 0, h to the n. But good enough. They all have lots of h's in them. They'll all go to 0. And so what we get is our power rule that says that the derivative of x to the n is going to be n times x to the n minus 1. I want to highlight that even if n is negative, we're subtracting 1 from it. We're not getting 1 closer to 0. So you can see this. You can make a nice table if you look at f of x and then f prime of x. And you do a bunch of limits, you'll start to see this pattern. And so x to the first ended up being 1. X squared, the derivative ended up being 2x. X cubed, you end up getting 3x squared. X to the fourth will end up being 4x cubed. And you might say, well, that doesn't look like what we talked about, but that's 2x to the first. That's 1 times x to the 0. It really does fit that pattern. Even x to the 0, which is 1, a constant, is 0 times x to the negative 1. But that's just 0, which is the constant rule, because that's just 1. But remarkably, this still works for things like x to the 1/2. That will be 1/2 x to the 1/2 minus 1, which is 1/2 x to the negative 1/2. And if you went through recognizing this is square root, and you went through limit as h goes to 0, square root of x plus h minus square root of x over h, you will indeed, after multiplying by the conjugate and all that, you will end up at 1 over 2 square root of x, which is 1/2 times x to the negative 1/2. It really is the same thing. The beauty of this is now the algebra for x to the 1/3, the cube root, for doing the limit was going to be horrendous. But now it's just 1/3 x to the negative 2/3, negative 2/3 being 1/3 minus 1. This will even work for something like 1 over x, which is x to the negative 1. That'll end up being negative 1 x to the negative 2, which is negative 1 over x squared. Again, if you work through the limit of 1 over x plus h minus 1 over x over h, you went through all of that mess, it will work out. It will land you there. But this is much shorter. And even if it's like x to the negative 5/3, whatever, it doesn't matter what that power is. Negative 5/3, x to the negative 5/3 minus 1 is negative 8/3. The powers get lesser, not closer to 0, but lesser. Right. That is the constant rule and the power rule. I'll just write them one last time. Our constant rule is that the derivative of any constant function that always just gives you a number out of it, the same number every time, it constantly gives you that c. That derivative is 0. And our power rule is that the derivative of x to the n is n times x to the n minus 1. One last note, I want to highlight how x is at the base and the number is in the power. If it had been the other way around, n to the x, we couldn't use this. So if there had been any x's in that power, we can't use power rule. We've got to do something fancier. That's a topic for another time. Thank you.